Okay, Chem 121, we're gonna work on Module 2 today, which is going to be basic ideas about matter. This is also a section that is found in Chapter 1 of our CHO textbooks, but without further ado, let us go and start talking about matter. Okay, so chemistry is all about matter. So in this section, we're going to learn a little bit about atoms, elements, and molecules. When I define chemistry, I am thinking about the study of the composition, structure, and properties of matter, and on the energy consumed or given off when matter undergoes a change. Matter and its behaviors is the central focus of chemistry. So what is matter? Well, matter is anything that occupies space and has mass. Mass is defined as the quantity of matter in an object. And when we look at energy changes, in this context, we're looking at energy as the capacity to do work. So what are atoms? Atoms are the basis of all matter. But what are they exactly? So let's think about this. If I cut a piece of graphite from the tip of a pencil, and I just keep getting smaller and smaller and smaller. So I'm cutting it in half, and then in half again, and in half, and in half, and so on and so on. How far can I go? Can I divide it forever? Well, eventually, I'm going to yield individual carbon atoms. And those atoms are composed of atomic particles, subatomic particles, and those can be split. Everybody knows that the atom has been split. There, if you read anything online or you watch Big Bang Theory, you're going to see that we've got all kinds of subatomic particles, far more than the ones that we usually think of in terms of atoms, which are protons, neutrons, and electrons. But if I look at the atomic level, I can only go so far where carbon is still carbon. So the word atom comes from the Greek atomos, meaning indivisible. I cannot divide a carbon atom into smaller pieces and still have carbon. A carbon atom is the most fundamental unit of the element carbon. Atoms compose all of ordinary matter. If you want to understand matter, you have to begin by understanding atoms. So we define atoms as the submicroscopic particles that constitute the fundamental building blocks of ordinary matter. Atoms can be combined into molecules. Free atoms are actually rare in nature. Instead, they're going to bind together in specific geometrical arrangements which form molecules. Water is a molecule. Water is H2O. It has 2 atoms of hydrogen and 1 atom of oxygen to make 1 molecule of H2O. Now, let's look at this. Here I have water, and here I have hydrogen peroxide. Now, I think we're all familiar with water. I have 1 oxygen atom, 2 hydrogen atoms. The distances between atoms, the geometry of the bonds, Those characteristics determine the properties of water. It's very stable. We bathe in it, we drink it, we swim in it. Hydrogen peroxide is much different. Here, the chemical composition is a little bit different. I have 2 oxygen atoms, and then I have 2 hydrogen atoms. I have hydrogen, oxygen, oxygen, hydrogen. That is hydrogen peroxide. Now, what do we know about H2O2? We know it's used as an antiseptic. You can buy it at the grocery store, and maybe when you were little, your mom would pour some if you skinned your knee and it would start bubbling. It's unstable. In a more concentrated form, it's going to burn on your skin on contact. It's also used in rocket fuel, and it's a powerful oxidant. It can actually bleach hair. So what's the difference between these 2 molecules? The addition of an oxygen atom. That's the difference. H2O is a combination of hydrogen and oxygen. H2O2 is a combination of hydrogen and oxygen, but how they're connected actually causes really, really different molecules that have really, really different properties. Now, states of matter are probably things that you've considered since way back when you were in elementary school. And what we learned that solids have a definite shape and a definite volume. We learned that liquids have a definite volume, but it can flow. So it'll actually assume the shape of its container. So if I take my cup of coffee and I pour it into a bowl, if I have, let's say, 500 milliliters of coffee, I'll still have 500 milliliters. The volume doesn't change. But instead of being in the shape of a coffee cup, now it's in the shape of a bowl. Gases or vapors neither have a definite volume nor a shape. It expands to fill its container. So it assumes the volume of whatever container it's in, and it also assumes the shape of whatever container it's in. I can change state or phase change. And this is when I have a transformation from one state to another, and this is the addition or the removal of heat. So if I take ice, I have solid water. But if I let it warm up, right, if I add energy, that water will melt and become liquid. If I heat liquid water up to its boiling point, which is 100 degrees Celsius, it'll phase change and it'll go from a liquid to a gas. So the addition of heat allows my water to go from solid to liquid to gas. If I cool it, like if you take your water and you put it in an ice cube tray and then you put it in the freezer, I'm removing heat, I'm cooling it, and then I end up with solid ice. So those are examples of changes of state. Now, the structure of these substances are different in solids, liquids, and gases. I have the same chemical composition, but the atoms or molecules have different structures because of the phase. This leads to different properties. Solid matter, you can see, is highly ordered, and all my molecules are very close to each other, very little space between them, and they are really tightly packed and they don't assume the shape of the container. When I go to liquids, my molecules are farther apart from each other. So solid to liquid, my molecules have gotten farther apart. They're moving a little faster. They can flow past each other. They can assume the shape of the container because of this flow, but they're still relatively close together. So that's why I don't have any appreciable change in volume. Now, when I go to a gas, my molecules are far apart. They don't even notice each other. They don't see their neighbors. They are whizzing around. They're really high kinetic energy. That's like a comet tail that you can see on the gas. This is very high kinetic energy. This is very low kinetic energy. I have very little motion here, mid-range motion and fast motion in terms of when I go from a solid to a liquid to a gas. So, solids, packed very close together. I have fixed location. They will vibrate, but they don't move around or past each other. They're just gonna sit there and sort of wiggle, right? They're just vibrating, but they're not translocating. They're not sort of moving past each other. Because of that, I have a fixed volume and a rigid shape. So ice, aluminum, diamond, those are all examples of solids. There are two different sort of structural components to solid. My solid can be crystalline, where I have very long range repeating order, such as the example of the diamond here, or I could be amorphous, where my molecules do not have any long range order. Glass and plastic are examples of amorphous solid. They're solid, but their structure is rather haphazard and not quite as ordered compared to a crystalline material. When I have liquids, they're packed together. Those molecules are packed together pretty closely, but they are far enough apart where they can move relative to one another. So this is my flow. They can go past, they can sort of flow freely, which gives liquids a fixed volume, but not a fixed shape. They can assume the shape of the container. So liquid water, alcohol, gasoline, those are all substances that are liquids at room temperature. In gaseous matter, I have a lot of empty space between those atoms. They are far apart. They don't even see each other. They are totally free to move. High order degree of motion. It's because of this that I can say that gases are compressible. Solids. If I have a solid in this chamber, they're already really close together. I exert pressure on that piston and they can't get any closer together. So they're not that compressible. I don't have a change in volume because I'm already pretty packed together and there's really no place for those atoms or molecules to go. In a gas, I have all this empty space here. So when I apply pressure, I can really pack them together. That makes them compressible. I can squeeze out that space. I can force them to get closer and closer together. So I can really change the volume. I can compress the gas. When you buy propane for your gas grill, you buy liquid propane. That is propane, which is normally a gas at room temperature and atmospheric pressure, which has been compressed into its liquid phase where I can get a lot of molecules close together. And then as I open the valve, that propane is coming out. As it's released, it's changing to its gaseous form, and that's what's burning in your gas grill. So these phase changes, they're dependent on how closely together these atoms and molecules are packed, and they're also dependent on how much kinetic energy that I have in here. If I go from a solid, which is highly ordered, to a liquid, that's called melting. So I'm adding heat. Anytime I have a red arrow going up, I'm adding heat. Here I'm removing heat. I'm getting colder, so it's blue. If I go from a liquid to a solid, that's called freezing. So we know that, we've experienced that with water. I can take my liquid water and freeze it into a solid, which is ice. I take my ice and leave it out at room temperature. It'll melt into the liquid phase. Here's another set of phase change. I can take a liquid and go to a gas. I have to add energy to break those molecules apart from each other. I have to increase the space and get them to move faster. So if I add heat and I go from a liquid to a gas, that's called vaporization. And if I remove heat and I cool it, I can actually condense the gas into the liquid. If you ever have, the air has humidity, it's a hot summer day, I take a really nice cold glass of ice water and I put it down. Well, there's air molecules, or there's water molecules in the air. It's part of the humidity of the air. Those water molecules in the air hit the surface of the glass because they're part of the air. They condense, and all of a sudden you've got that condensation, that water sort of pouring, down the outside of your glass because it's cooling the water molecules that are in the vapor phase in the air, and it is condensing them into liquid water, which then is going to run down the side of your glass. Now, I can go directly from a solid to a gas. If I do this directly, this is called sublimation. This is dry ice, which is solid CO2 goes to gaseous CO2. And if you've ever used dry ice to pack a cooler or you've played with it in science class, what you're going to notice is that I don't go through the liquid phase. As I go at room temperature under atmospheric pressure, I go from a solid to a gas. So its natural state at room temperature is very, very cold, dry ice. It's very, very cold. It's cold enough where it can actually burn you. So if I add heat, I'm going to go from the solid to the gas directly. Now, if I remove heat, I can actually do the opposite phase change. Going from a gas directly to a solid is called deposition. I deposit the solid, it's deposition. We're going to talk a lot more about this at the end of the class when we look at phase diagrams and we look at heating and cooling curves and we look at these processes in a lot more detail. But at the moment, what we have to do is just understand how these states of matter, how these are related to one another and how phase changes occur and what does that mean. Now, I can also classify matter into different types. I can have a pure substance where I have the same physical and chemical properties throughout. This is important. Pure substances cannot be separated into simpler substances, and I'm actually going to highlight this in red, by a physical process, right? Physical means I'm not altering the chemical identity of the substance. I can also have a mixture, which is a combination of two or more pure substances. This is really important. So I'm going to put this is how I differentiate between the two. If I have two pure substances, I can actually separate them by physical processes. If I have salt water, I take some salt, I put it in some water, I stir it up, the salt dissolves in the water. Salt is still the salt, water is still the water. Each one of those, the salt is a pure substance, the water is a pure substance, right? I put them together, they're dissolved in one another, that creates a mixture. If I leave my glass of salt water out on the open to the air, at some point my water is going to evaporate, which is sort of like going into the vapor phase, and then it is going to diffuse away. But what I'm doing is I'm separating the water from the sodium chloride, the salt, based on a physical process. The water stays water, it just goes into the gas phase and diffuses away. The salt is still salt, it's now going to be separated from the water because it can't diffuse away because it's not going to phase change under regular atmospheric ambient conditions. So, what is a physical process? This is a transformation of a sample of matter. It could be a change in the physical state, and this is really important. It does not alter the chemical identity of any substance in the sample. So that substance remains the same chemical substance. If I go from ice to liquid water to gaseous water, water is still water, it's still H2O. It hasn't changed composition. That is a physical process. Okay, let's look at pure substances. There are two different types of pure substances. I can have an element, like off the periodic table. This cannot be separated into simpler substances by chemical means. This is where I alter the chemical composition. So I cannot take sodium and make it something else, right? I cannot alter it. I cannot put it into any simpler substance by any chemical process. I can also have a compound. Now here it's composed of two or more elements that are bonded together in fixed proportions. It can be broken down into individual elements, and this is by chemical means. So I can take H2O, and if I add electricity, I can actually get hydrogen, elemental hydrogen plus elemental oxygen. Is this water? No. Water is no longer water. I've broken it down into its constituent elements by doing a chemical reaction. This isn't a phase change. This is actually changing the identity of the substance. Now, if I have mixtures, there are two types. I can have homogeneous mixtures. Here, this is the key word. They're distributed uniformly. My components in my mixture, I have two or more substances that are pure, right? Two or more pure substances. They're distributed uniformly throughout the sample. I have no visible boundaries or regions. It can also be called a solution. Kool-Aid is this type of a mixture. Coffee, tea is a homogeneous mixture. If I look at Kool-Aid, I take that packet, which has all those solids in it, I add it to water, everything dissolves. It's a mixture. I have water and I have all those components that are in that Kool-Aid packet, but now they're distributed uniformly. I can't, like maybe the color's red. It's gonna be red Kool-Aid. It's opaque, or it's translucent. I can see through it, right? But I can't tell that there are any boundaries to the components. Everything is dissolved into the solution. I can also have a heterogeneous mixture. Here I have not distributed uniformly. I can have distinct regions of different composition. This is what I call my chicken noodle soup. I have some broth, I have some fat, I have some chicken, maybe some carrots, maybe some celery. I clearly have many, many substances mixed together, and I can see them. I have distinct regions of those different substances. So here's a flow chart. I have all matter. I can distinguish all matter and break that down into either pure substances or mixtures. Can it be separated by a physical process? Yes. Two or more pure substances together I can evaporate the water, get the salt out. No, I have either an element or a compound. Here, I can separate using chemical reactions. Elements I can't. That's at the lowest fundamental unit. Think about the elements on the periodic table. Compounds, yeah, I can take water and I can separate it into hydrogen and oxygen as constituent elements, but it has to be done by a chemical reaction. I have homogeneous mixtures, which are uniform. And then I have heterogeneous mixtures where I can see distinct boundaries. This is my vinegar, right? I can't see any difference in the vinegar. The vinegar looks the same throughout. But if I have my Italian salad dressing here, I have oil, I have water, I have different types of spices and whatnot, I can clearly see that multiple substances are mixed together and they form distinct boundaries from one another. Now, we use these diagrams a lot in this class. You have to be able to analyze what's happening in these diagrams. Here, I have single atoms. All of these are blue balls. It looks like they're in the gas phase because I have the little comet tails going on. This is a pure substance because all the atoms are identical to each other. Here, I have fixed ratio. I have a black to 2 reds. I have a black to 2 reds. This is actually carbon dioxide. This is also a pure substance, but this is a compound because I have more than one element combined in a fixed ratio. I can get the carbon out, I can get the oxygen out by chemical means, but it's still a pure substance because unless I do chemistry, I can't separate the carbon from the oxygen. This is a mixture. I have maybe some nitrogen here, I have some hydrogen here, I have some oxygen here. I have different molecules of different atoms, and I have the blue 2-atom molecules and the white 2-atom molecules and the red 2-atom molecules, which suggest I have mixtures of 3 different substances and their gases. I see this comet tail here. These are all gases actually, but this would be a homogeneous mixture because they're uniformly distributed. I want to think of air, right? Maybe I have oxygen, I have nitrogen, here I have hydrogen. Those are all going to be mixed together, but I can't distinguish where the oxygen starts and the hydrogen starts, right? That's going to be a homogeneous mixture. So be able to read these types of atomic diagrams because this visualization is really important as we go forward in this class. Now I can separate mixtures, right? This is mixtures. I can separate mixtures by physical means, right? By using physical properties in order to get them to separate. Let's say I have a mixture of something that is a solid mixed in a liquid. Well, I can use filtration. If I do this, what I'm doing is I have my funnel, I have my filter paper, here's my solid in my liquid, right? So I have a liquid and a solid. I am putting this into here. The solid is staying on the filter, and then the liquid is going here. So my filter paper is trapping the solid, my liquid passes through. I just separated the solid from the liquid. That's called filtration. Notice this is a ring stand here. If we're in the lab, we're not this semester, here I have a clamp that holds everything together so nothing wiggles around and it can't fall over. This is a filtration apparatus. This is gravity filtration. I am not pulling on the liquid. I'm just using gravity to have that go through the filter paper and then go ahead and get collected in that beaker on the bottom. Let's say I have two liquids. I can use distillation. I can separate the more volatile component from the less volatile component by using boiling point. Here I have two liquids. As I heat this, the liquid that has the lowest boiling point, those atoms are going to rise up. They're going to form a gas and go up my, tube there. This is water. This is cooling water. So this is colder. This is going to be the gas form. Once it hits here, it's going to condense back into the liquid form, and then it's going to dribble down into here. Well, as long as I'm at the lower boiling point of that more volatile substance, that's what's going to be rising up. The higher boiling point substance is going to remain in that flask. So I can actually use distillation to separate something that is more volatile from something that is less volatile using the difference in their boiling points. If you've ever taken biology, you've probably done centrifugation. This is the process for separating particles by applying a centripetal force. So I can have sort of a sedimentation of heterogeneous mixture. Here I have different layers in the substance. And you know, you've probably all seen that centrifuge where you spin it around and it has to be balanced. But this is a good way to sort of force things to separate by applying the centripetal force. There's also a method of separation called electrophoresis. Again, this is used a lot in biology. It's separating molecules based on their charge and size. So this is really good for DNA, for proteins, things like that. Maybe you guys have used this in biology as well. But all of these techniques are using physical means, using some physical property that is different between the substances that you want to separate, and using those differences in order to affect the separation into the various substances that had composed the mixture. I can also describe properties of matter. I can have intensive properties, which is independent of the amount of substance. All right, if I have the color or the melting point, those things don't change if I have more or less of the substance, right? I could have a lot of gold and it's still gonna look yellow. I could have a little bit of gold and it's still gonna look yellow. I can have ice, it's still gonna melt at 0 degrees Celsius. Even if I have a little bit of ice or a lot of ice, that melting point doesn't change. That's an intensive property. An extensive property varies with the quantity. So volume, I can have more or less. I could have 500 mils or I could have 1,000 mils. That is an extensive property because my 1,000 mils is a lot more space. Mass, the amount of matter that is present, is also extensive. So let's get back to physical versus chemical. Physical properties. I can observe these without changing it into another substance. So the composition stays the same. So luster, hardness, color, the state, is it a solid, liquid, or a gas? What is its melting point? What is its boiling point? What is its density, which is the mass per unit volume? These are all examples of physical properties. I can observe them without affecting the composition, the chemical composition of the substance. I can contrast that with chemical properties. This is observed only by reacting it to form another substance. This is where I change the chemical composition. So if something is flammable, when it burns, it's going to change into different substances. If I take wood and I burn wood, I don't have my wood left. I have that carbon soot, and I've also made carbon dioxide and water and other substances like that. So here's examples. Physical properties are things I can describe, right? The temperature, the color, the melting point. Is it conductive or not? How much of it do I have? The odor, the solubility, the hardness, right? Chemical properties. If I rust, if iron rusts, I change into iron oxide. I'm no longer iron, now I'm iron oxide. When I combust gasoline, I form carbon dioxide and water. If I tarnish silver, I have an oxide of silver. If I cook an egg, I'm actually changing those substances. I'm denaturing some of the proteins which cause them to solidify and change into different substances. I'm degrading it, and I actually form new substances that have new chemical identities. So those were the properties. Think about the change. This is actually the change that alters only the state or appearance. My composition is the same. So a change of state. If I freeze something, if I boil it, the actual change that goes and looks at a physical property is actually the physical change. Or I could have a chemical change. This is the process of rusting. Rusting is a chemical property. The actual process of rusting is the chemical change. And again, the key here is that alters the composition of the matter. So when water boils, it changes state. Those bubbles actually have vaporized water in them. So that I'm adding heat, right? I'm actually going to go from liquid to gas water molecules, right? So my water molecules are here. They're just farther apart, moving faster. That's steam, right? You can tell that that's the gaseous form of water. Is it still water? Yes. I still have H2O. Just like in the liquid, I still have H2O. I've just physically changed it from a liquid to a gas. So this is boiling. That is a physical change. When I look at chemical chess, here's my iron. This is my iron nail. You'll see this coating on this? That is rust. Rust, actually, if this is my iron atoms in a lattice here together, that's all iron. Now I have iron, whoops, connected to oxygens. So now I have all this oxygen in here. This is an oxide. It's a different substance. So my atoms have rearranged, and I've made it, the original substance, into something that has a different chemical composition. That is the chemical change. So if I look at this diagram, dry ice subliming, gas to liquid. It's still CO2. That's a physical change. I still have CO2 molecules. Now they're just in the solid form here to the liquid form there. That's going to be a phase change. That's a physical change. Here I have sugar dissolving. So I go from the solid phase, but now it's dissolved, so it's separated, but it's separated by water molecules. I have not altered the composition. My sugar molecules are still here. My sugar molecules are still intact. Now they're just separated by water. So this is a physical change. The water's the same, the sugar's the same. They're just dissolving one another. I go from the solid state to the aqueous phase, which is just means dissolved in water. Here I have propane gas burning. Well, look at this. Here's my propane molecules. Now I'm forming carbon dioxide and water. Notice I have got different substances. I start with propane and oxygen. I end up with carbon dioxide and water. These are different substances. My atoms have rearranged and formed new substances. My carbon is now part of carbon dioxide. The hydrogen and the oxygen is part of the carbon dioxide and the water. So I've taken my propane and my oxygen, I've broken bonds, rearranged atoms, and then reassembled them into new chemical substances. That is a chemical change. All right, that's the end of module 2. We have one more module in this week, which is module 3, going over atomic theory. But until then, I will see you, and I will talk to you again soon. So happy studying, and I will be back.